In this video, we're going to talk about how to solve systems of equations by graphing. So what is a system of equations? A system of equations is two or more equations that model different aspects of a common situation, and the solution is any point that they have in common. Possible number of solutions to a system. So sometimes there's one solution, sometimes there's no solution, and sometimes there's infinitely many solutions. Those are our three options when we have systems of linear equations. So when we have one solution, that means we have two intersecting lines and they touch exactly in one spot. So that's when we have one solution. Another option is we have no solution because the lines will never touch, but that means that those would be parallel lines. And then sometimes we have infinitely many solutions because the lines are actually the same line and they touch like everywhere because they're the same. Let's look at an example. If they say, is 3, 4 a solution to the following system? Then what we can do is check it by plugging in that input of 3 and that output of 4. So let's plug in x equals 3, and then let's plug in y equals 4 and see if they would work for both. So 2 times x, which is 3, plus 3 times y, which is 4, we're going to check and see if that is actually 18. So 2 times 3 gives us 6. 3 times 4 gives us 12. And then 6 plus 12 is 18. So that works for our first equation. Let's check the second one. So y equals x plus 1. We got y equals 4 is our output. So plug that in. X is 3. So we'll plug that in for the x. So is 4 equal to 3 plus 1? Yes, it is. So since it works for both equations, so let's write that down. Because the point works for both equations, it is a system, it is a solution to the system. So that's a good way to check and see if a point is indeed a solution. So let's look at the next part. It says steps to solve a system by graphing. Solve each equation for y is our first step. Number 2, on the same graph, use slope-intercept form to graph each equation. Remember to plot the y-intercept first and then use the slope to rise and run to another point. And then step 3, look to see where the two lines cross. Write your solution as an ordered pair. So if we just want to identify the solution and it's already been graphed for us, we just would pick out where they touch. So I see they can touch right here. And from the origin, I have to go right 2. So x would equal 2. And then I have to go up 1 to get to that ordered pair or that coordinate that identifies that solution. So the solution to this system of equations is the point 2, 1. For B, I have two parallel lines, so they're never going to touch. So we would say there's no solution to this system. And we can also write that as a 0 with a slash through it. Let's look at a few more. So if we're going to solve this system by graphing, and we're given number 1, y equals 2x minus 3, and y equals x minus 1. We want to graph by starting with the y-intercept. So on this first equation, I'm going to plot this one in blue. I'm going to start with the y-intercept, which is the negative 3. So go down negative 3 on the y-axis. Then I'm going to use a slope of 2, but really that's equal to 2 over 1. So we're going to rise 2 and run 1. So from my y-intercept, I want to rise 2 points and run 1. So 1 to the right, and that's all positive. So up 2, right 1, up 2, right 1. That gives me several good points where I could graph this line. Now I'm just going to erase these points that help me get my line because I don't really need those anymore. Now let's graph the second one in red. So y equals x minus 1. We have a y-intercept at negative 1. So first plot that point. That's always our starting point. And then we have a slope of 1 over 1. So from that y-intercept of negative 1, go up 1 and right 1. And then up 1, right 1, and do that a couple times. And that just helps you to draw a nice straight line that goes with that equation. So we can tell where they touch is at the point right here, which looks like it would be 2, 1. So we can just pick that out and write it as an ordered pair. Let's look at another one. Number 3 is the next one I'm going to do. It's not as straightforward. So first we need to solve for y because they're not already equal to y, but it doesn't take a whole lot of work. We just got to move the x to the other side, and it's adding because there's no sign in front. And remember, if there's no sign in front of the x, it's like a positive. So I have to subtract x to move it to the other side. And then I get y equals negative x plus 3 for that first one. For the second one, the same thing is happening. I have a positive x, so to move it, I need to subtract it. And then I get y equals negative x minus 1. We always want to write it in slope-intercept form so we can graph it like we did the last one. So I'm going to graph this first one in blue again. I have a y-intercept at 3. Let's start with that one. So 3. I have a slope of negative 1 over 1. So I'm going to go from that y-intercept down 1 and then right 1. Down 1, right 1. So you only want to do one negative move. If you go down and left, you've done 2 negatives. So you don't want to do that. Only one negative. So for this other equation, let's graph the y-intercept at negative 1 and then use our slope. So we have negative 1 over 1. So from that point, we can go down 1, right 1, down 1, right 1. And we can see that they have the same slope, and so they're never going to touch. So let's jot that down. They have the same slope. They're parallel lines. Those are the types of lines that have the same slope, and therefore they have no solution because we'll never find a point where they intersect or touch. And we can write that as a 0 with a slash through it. So that's it for number 3. Let's look at one more thing in this video. Without graphing, determine whether the following lines would have no solution, infinitely many solutions, or one solution. So what we can do is look at their slopes, and we just got to get them equal to y in order to check it out. So the first equation is y equals 3x minus 5. So that one is already in y equals. The second one says 2y equals 6x minus 10. So I need to solve for y by dividing by 2 so that I can move that 2 over. It's multiplying the y, so I need to do the inverse operation and divide by 2. And I get y equals 3x minus 5. So what we notice here is our first equation was y equals 3x minus 5. And now the second one actually is the same. They didn't look the same in the beginning, but now they do. And so when they are the same, let me get my pen. When they're the same line, they have infinitely many solutions because they will touch everywhere. So let's write they're the same line, and therefore they have infinitely many solutions because they touch everywhere, everywhere, everywhere. So let's look at number 2. Y equals 1/2 x plus 7, and then let's solve this second equation for y. So I have negative x. I need to move it. So I'm going to add, since that's the inverse of subtracting. Then that will go away, and I have 2y equals x plus 6. Then I have 2y, so it's multiplying the y, so I need to divide, because that's the inverse of multiplying. And I get y equals 1/2 x plus 3. So let's examine what we've got now. Our first equation was y equals 1/2 x plus 7. And now our second equation is y equals 1/2 x plus 3. So they are not the same line, but they do have the same slope. So let's jot that down. Same slope. So visualize, if they have the same slope and I were to graph them, they would be parallel lines because that's the ones that have the same slope. And therefore, they're never going to touch. And so they have no solution. And then we can write it as a 0 with a slash. So that's it for our first